Welcome to Ask and Learn.
We are given two intermediate reactions for the overall reaction used to prepare nuclear fuel. We want to determine what the change in Gibbs free energy is of the overall reaction at 85 degrees Celsius. So the first thing that we need to do is combine these two reactions by adding them together in order to first write out that overall reaction. We can see that UF4 cancels out on each side, and so the overall reaction is UO2 solid plus 4HF gas plus F2 gas goes to UF6 solid plus 2H2O gas. And now we need to determine the delta G of this reaction at 85 degrees Celsius. Because the temperature is not at standard conditions of 298 Kelvin, we cannot directly solve for delta G by finding the overall change in Gibbs free energy of the products and subtracting that same value for the reactants. Instead, we need to use this equation since it relates temperature to delta G through delta H and delta S. And we are given values in the problem for delta H and delta S, and we can use the appendix in order to look up those values for the ones that aren't given in the problem statement. So these are the two equations that we are going to use to find delta H of reaction and delta S of reaction, so that once we find them, we can plug them into this equation at the temperature of 85 degrees Celsius to find delta G at that temperature. So for delta H, we first find the total change in enthalpy of the products and then subtract the total change in enthalpy of the reactants. For the change in entropy, delta S of the reaction, we find the total entropy of the products and subtract the total entropy of the reactants. So starting with delta H, we can break up the change in enthalpy of the products and reactants into two different expressions to help us organize our work. We start with the reactants. Again, we are going off of this overall equation now. We start with the products, and we see that we have 1 mole of UF6 and 2 moles of H2O on the product side. So 1 mole of UF6 and 2 moles of H2O. We are given this value for the delta H of UF6. We can look up this value for the delta H of H2O in the appendix. And again, these correspond to the standard change in enthalpy of formation of each one of those compounds. And so when we cancel off units of moles, we are left with energy units of kilojoules for the change in enthalpy of the products. And since we added the total enthalpy change of each one of the products and add them together, that is the total enthalpy change of all of the products. And now for the reactants, we have 1 mole of UO2, 4 moles of HF, and 1 mole of F2. But remember that for delta H values, we use delta H of formation at standard conditions in order to help us determine the overall delta H. And F2 is a naturally occurring diatomic gas molecule that has a delta H of formation value of 0. So we only include the reactants of 1 mole of UO2 and 4 moles of HF for the delta H for the reactants. So 1 mole of UO2 and 4 moles of HF, we look up their values for delta H of formation at standard conditions. We multiply them by the number of moles of each and then add them together to get the total change in enthalpy of the reactants. And now we do the total enthalpy change of the products minus the total enthalpy change of the reactants. And this is the delta H of reaction that we should find. And now we use the same process to solve for delta S of reaction. Starting with the products, we have 1 mole of UF6 and 2 moles of H2O. So 1 mole of UF6, 2 moles of H2O, each multiplied by their standard molar entropy values, which we can look up. And when we cancel off units of moles this time, we are left with joules per Kelvin, or units of entropy. And when we add those overall entropy values together for all of the products, we get the total change in entropy of the products. And then we find the total entropy of the reactants, seeing that we have 1 mole of UO2, 4 moles of HF, and 1 mole of H2, or of F2. So 1 mole of UO2, 4 moles of HF, and 1 mole of F2. Multiply each one of those by their respective standard molar entropy values, which we can look up. And when we add them all together, we get the total entropy of the reactants. Now we take the total entropy of the products minus the total entropy of the reactants, and we get the total change entropy of the reaction. Now that we have delta H and delta S, and we want to find delta G at a given temperature, we can use the equation delta G equals delta H minus T delta S in order to solve for that value. So delta G equals delta H, which we calculated to be negative 503.625 kilojoules. So negative 503.6 kilojoules minus the temperature is 85 degrees Celsius. When we convert that into Kelvin, it's 358. We multiply that by the delta S, which we just found, but we should convert this into kilojoules by dividing by 1,000, so that we can subtract the units of kilojoules from the delta H value. And so that's negative 371.9 times 10 to the negative third kilojoules per Kelvin. We cancel off units of Kelvin after we multiply those two together. We are left with units of kilojoules for delta G. And when we do the math, we should get a final answer for the change in Gibbs free energy of this reaction at 85 degrees Celsius to be negative 370 kilojoules.